7:15. Let's see. Last time we started talking about inductors, capacitors, and that was the end of. So we continued on. A quick talk about safety, a quick talk about units, more resistors, series parallel circuits, a refresher on Kirchhoff's laws, and then other passive components. So tonight we'll start off with inductors again, and we'll go to switches and capacitors and resistors and the practicality of use and some of the things that we do most often from a maker point of view. So first off, we'll talk about a quick thing on resistors. Long time ago, resistors were expensive. They were hard to make. It was a real breakthrough in, I think, the 60s when they were able to actually make resistors be reliable. Or maybe it was the late 50s, and it has to do with the hook in the middle and how you bond it to the posts on the end that are going to be the leads. It was really fragile. So you could buy, if you make any component, there's usually a distribution curve, right? A Gaussian curve around the middle. And this is the value target, my target value, right? And so let's say, I don't know, I want to make a 1 ohm resistor because that's nice and easy. Or some ohm resistor. And so there's some probability that they're going to be within 1% tolerance. So if it was, let's use 100 ohms, 1% tolerance here would be 99 to 101 ohms. And then there's some probability of 5%, so 95 to 105. And then out here, 10%, 90 to 110 ohms. So when you design sensitive circuits, you've got to pay attention to these things because you have, if you say, oh, I want a 100 ohm resistor, you're never going to get a 100 ohm resistor. It's going to be 100 point something or 99 point something. Back in those days, people would try to be cheap and go, oh, we'll go buy 10% because most of them, if you do a 10%, you got to do more math to make sure things are going to work in an active circuit as opposed to an analog circuit as opposed to a digital. But people would think, but if I look at it, the distribution, I'm going to get some here, so most of my parts are going to be good and whatever. No, it's like when they've been processors, right? If you bought a 10% component, what you got was all of these components, and they cherry-picked all the good ones out. So these would be like, I don't know, $1 each. A 5% would be like $2 each, and a 1% would be like $10 each. And so if you bought a 1%, you were guaranteed this, but if you bought a 5%, you were guaranteed actually this sort of a cylinder here around the outsides. So it's something to keep in mind, but these days I almost never see a 5% resistor. Everything's 2% or better, and precision resistors are easy to get where it's good to like 0.1% or whatever, and they're not horribly expensive. Now there's color coding. I just talk about this. So if you're looking at a surface mount resistor, right, it just looks like this. And when you look at, and this is true for all of the passive components, there's common footprint numbers. So what you look at on the underside is there's a solder pad that kind of comes around like this on either side, and when you mount it to the circuit board, you've got a spot that looks like this. And so these things will come down and land, and your chip will sit right here like this, and the solder flows underneath of it and holds it onto the chip. I don't have a circuit board I could show you right now, but I've got a bunch, but I didn't think to bring one. So these come in footprints, and so there's like a 06, 04, 04, 02, 08, 06, and there's, what this is the first dimension in millimeters and the second dimension in millimeters, I think. So you little big freaking chips. I made the mistake, I think everything I was doing was 06, 04s, which are literally about that big. And I got some, I think I picked up an 0201 by accident because I was looking for the cheapest, and it was literally, it was smaller than that. Shit, I can't solder that for the crap, right? So keep an eye out if you're doing surface mount, which is unfortunately for makers, most stuff surface mount now. It's hard to find. It's not hard to find through hole parts, but they're more expensive. They're less dense on the inside if you're talking about processors and things like that, or less I/O, just because, you know, if you're talking the standard dip packet, which I actually have one of those right here. Hang on. I just bent the back legs. That's a standard dip plastic. That is a 100 mil pitch, so 0.1 inch pitch on the leads. Those are easy to solder by hand. You've seen these, I guess. So I'll bring this up here to the thing because I don't know if you people at home can see it. So you see my finger. I bent the back two leads, but each of those pins, this is what's called a through hole component, and they're each 100 mils. A mil is 1,000th of an inch, so 0.1 inch. And when you look on your circuit board, you'll see these little annular rings, holes, vias. 1, 2, 3, 4, 5, 6. So this would be a 12-pin dip, and you'll usually see something like this on the outline of it, and this notch lets you know that that's pin 1, not 7. 1. And so they all have markings on them of some sort. So this one very clearly has that notch, just like I was pointing out, like I drew up there. Some just have on the chip itself, there will be a dot right there. It says that's pin 1. And the leads basically come down right here on the sides and go down through the board. Easy to solder. You put them on the soldering iron on the back side. Done. Surface mount stuff, you usually use a solder paste, and then it goes in an oven. And I've actually built I have a, personally, I took a toaster oven, ripped it apart, put a process controller in it, and I can drop, you know, put my board together, you smear your stuff all over and place your part, stick it in there, hit the button. 5 minutes later, I've got a circuit board that's completely soldered. Then I spend a lot of time going through and doing touch-up because I put too much solder paste down and I balled up into a mess. Now, the older resistors, if it's not surface mount, look something like this, or sometimes little dog bones come out. And these are, again, the wires. You bend them however you need them. You can bend them straight down like this, or you can bend them around like that if you want to make space. There's good and bad about both. The bad about putting them up like this is they stick up high above the circuit board. There are also little antennas that pick up noise. but they don't take up any space. It's that much space. Whereas these guys, they take up more space, but they're more solidly mounted. They don't pick up as much noise. But what you'll see on them is there'll be color bands. And usually 3, and then you might used to see 1 or 2 more out here. And so the colors are, I'll tell you the mnemonic I learned, and it's bad, so don't repeat it, but here it is. It's bad boys rape our young girls, but Violet gives willingly. And this is black, brown. They were less PC days back in the 70s and 80s. Red, orange, yellow. There's another mnemonic that I don't know. I've heard it like twice, and this one was already cemented in my head. So, green, blue, violet, gray, white. And this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so let's say this was a brown, black, red. That would be 1, 0, and 2 zeros. So it'd be like a kilo ohm. Simple. Or maybe I might have that wrong. It might be 100. It might be 1.0. Anyway, I don't use them anymore. Anymore, you get them in a little pouch when you buy them from DigiKey. They come in a pouch. It's labeled. Most of the time, they don't have them on there. You might look at it, and it might have the number actually stenciled on it if you've got a magnifying glass. So I don't use them anymore. Oh, and then you'd have these bands would be tolerance bands. So it'd be gold would be a 1%. Gold was a 5% and silver was a 10%, or maybe it was a 1% and a 5%. I don't remember. So, history stuff that probably don't care about too much. So we talked about inductors. So an inductor is literally a coil of wire. It goes around and around and around. It's all it could also be, sometimes you'll see them wrapped on a toroid. So you'll have a torus and with some dimension on it, right? And the wire will come in and it'll wrap around. Like that. So that's the iron core. You'll see these. So I talked about last week transformers. Put an AC signal in. I can get a different voltage out. So if I were to say put 120 volts AC here, and this were a 10-to-1 transformer, I would get 12 volts AC out here. Simple. Nice way to knock power down, knock voltage levels down. The other thing that happens here is you transform. So if I draw 1 amp on this, let's make it easier. If I draw 10 amps on this side, I'll be drawing 1 amp on this side. So conservation of energy, total power has to stay the same going through, minus some inefficiencies. It's like 98 or better % efficient. The other thing we can do is we can make oscillators with them and capacitors. The most common use, I think, well, there's two. If I've got a power supply and I've got a circuit that's, say, doing a lot of switching, it grabs energy and it gives it up, and it's not a level load, I can put an inductor in line with my power supply, and again, a capacitor here. Remember that feeds energy as we need it. By putting this here, this basically blocks that AC signal, right? Because inductors like to have DC. They are current memory, whereas a capacitor is voltage memory. So you get a certain amount of current through it, it wants to keep it there. When you change it suddenly, the voltage will change a lot, but the current won't. We did that with some graphs last week, if I remember right. I'll repeat that again, I guess, just for completeness. So if I've got inductor, voltage, time, how do I do this? Let's make that magnitude, and I'll do 2. If I change my voltage like this, I'll see my current do that. Whereas with a capacitor, the same thing. Let's see. Current. Voltage. With a capacitor, if I try to change my voltage hard, what I'll see is it'll ramp up, and then it'll. I did that backwards. No, I didn't. It'll ramp up, and then it'll ramp down. But my current will do the opposite. It will spike, and it will come down, and then it will spike. Actually, it'll spike the other way. Come out like that. Voltage differentials. These aren't quite right. I have to sit down and actually think about it a minute. But the practical side of that is it helps you smooth the supply, what it sees. So if you've got a power supply and you don't want it to be yanked around, because that's noise that gets back into other things if you're doing sensitive stuff. All right. Next thing we'll talk about then is a switch. A couple of different kinds of switches. There are a couple of different symbols. So you can see this is a switch, and it's kind of physically what it is. You push down, it makes a connection, bridges the two together. You can have a ganged switch. So anytime you see a ... like that, it means those two things are connected and they work together. Or you can even see, sometimes you see it drawn this way. Push down, that one closes, this one opens. Opposite of water, so this is one of the places where the water analogy breaks down. An open valve lets water go, an open circuit lets no current flow. A closed circuit lets current flows, a closed valve does not. But this is basically your water valve, right? You can also see them drawn this way, with an action like that, just to let you know. And if you ever see one of these, well, let's see, that could be headphones, or it could be a circuit breaker. If it's got that, it's a circuit breaker. Which is a kind of a switch, but it's a thermally activated switch. What makes it pop is when you draw too much current, it heats up and pops loose. And then when it cools down, you can reset it and you're good to go. So I always get this backwards. So this would be a single pole, single throw switch. And I believe this is a single pole, double throw. Can never remember pole or throw. I always get them backwards. But you can also do this. So this would be a double pole, single throw. Goes one way or the other, and then this would be a double pole, double throw. Things like that.
And you'll see those listed as SP, ST, whatever
Yeah,
the switches.
single SP, single pole, ST, single throw, DP,
Yeah.
DT, the whole list. Look at the circuit. I know I got it. I know I just told you it wrong. I know I got it backwards.
And it's all basically you push the button once and it does one thing. You push the button once, it does two things, basically.
Right, two actions happen.
Yeah.
They are mechanical actions.
Yeah.
An inductor can also be used as used in a relay. So the inductor creates a magnetic field. We talked about that last week. That's how it works. The current flowing through it creates the magnetic field. When the magnetic field collapses, that creates current. So if the current stays continuous, everything is stable and is at some point that it likes to be. As soon as you try and change the current, well, that magnetic field tries to collapse or increase, whatever it is, and that resists the current going through it. But when you, this is one of the symbols. This one's more graphic. Sometimes you just see this, and then you'll have the switch up here. In this case, when you put energy here, it closes the switch. That's a relay. That's really handy when you want to switch high currents, right? Your little microcontroller can give you 25 milliamps, but that 25 milliamps is enough to drive this coil, and maybe you've got a 10 amp circuit here, so you can control higher current, higher power loads that way. So that's why you would want to use this guy. Relays, especially when you get into higher powers, their failure mode tends to be this little set of contacts right here. They weld. They come down, they come off. There's a little arc that happens. Eventually they either weld or they get pitted and they don't make good contact and they just quit working. But they always fail right there. Almost always fail right there. So now we'll do switches. Well, practical use of switches.
And I guess a really common example of a relay would be like the blinkers in your car. You hear them go ka-chink, 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 ka-chink.
Those are... I don't know what modern ones are. I would not be surprised to learn that they've replaced it with electronics and then put a thing that sounds like the old blinker can.
Yeah.
The old blinker can...
Generally, relays are the things you hear go ka-chunk when things need to go ka-chunk.
Yeah. Well, and big relays are called contactors. Like for outside the building here to supply power, that'd be a contactor.
With that big switch I have at work that goes ka-chunk when you...
That's a contactor. And the reason they're big is you're pushing power through them. So we're going to get into the... Great segue. We're going to get into this right now. When a switch comes closed, it's a mechanical device, and it literally bounces. So it comes in, it hits, and then it opens, and then it hits again, and it may happen 10 times. What they're doing with those contactors is they've got it's like a big frickin' spring back here behind the piece of metal. It's going to come into place. And so what you're doing is you are pushing down on that spring and just, and then finally it breaks over and bam! Mm-hmm. And the idea is to get as little bouncing as possible.
Yeah, it's a kill switch.
Because when you're pushing kiloamps out there, that throws a big arc. And then there's that thing in the arc flash safety there where it causes fires, explodes, white noise everywhere, makes people's radios go for a second. Old ladies who are watching Wheel of Fortune, their TV goes for a second. Then the FCC gets mad at you, and there's all sorts of bad things. When you make noise like that, all sorts of bad things ripple out of that. Whether it's just the silly stuff that I'm talking about, or if it's weird waveforms coming in that blow up your TV and your equipment. So practically speaking, let's talk about very quickly a transistor, specifically a field effect transistor. The symbol is often this, and there's a couple of different symbols you might see that mean the same thing. I'm going to use this as just generic. So you have a source, a drain, and a gate. And in the logic that we see in our computers, basically what happens is this voltage level here is VGS, gate to source. This is V drain to source. and this is VDS. And I'm not going to get into the math in these, but there is a what they call VT, which is the so-called turn-on voltage. We'll say it's 1.2 volts just for S and Gs right now. So what happens is, if I say this is VGS and this is IDS, so this is the current, will flow in and flow back out like this. What happens is I increase this voltage from 0, nothing happens, nothing happens, nothing happens, and then it follows curve like that until you reach some saturation current, and then it kind of comes over like that. This is an exponential thing. You can see how if I was wanting to do an amplifier, I could do just a little bitty change here, and that would come up to a really big change there. That's how an amplifier works. You're just playing with these things. But what we use them most for is switches. So in your the simplest gate that's inside, the simplest logic gate, the symbol is this. An inverter, a 1 in gives you a 0 out, a 0 in gives you a 1 out. That's logically speaking. This would be 5 volts, gives you 0 volts out. 0 volts gives you 5 volts out. We use digital binary, and we use binary math when we do the design for all these things. Inside the circuit, what you see is 2 FETs. The output taken here. I'm using this notation. So this is the P FET, and this is an N FET. The one that I drew earlier was an N FET. And what this is showing is that there's no connection through. So this is not infinite resistance, but for all practical purposes, what we're doing, it's infinite resistance. It's also, remember we talked about 2 capacitive plates? There's a capacitance there. So if I were, what happens is if I put 5 volts here, this guy turns on, this guy turns off. He's sort of the reverse. This is his source, drain, gate. So if I put 5 volts there, I get a current path that looks like this. And if I put 0 volts there, I get a current path that looks like that. Now, if I imagine, for all intents and purposes, if I make this a black box, which is all we care about, right? I just thought I'd let you know that, because why not? If I look at this as a black box, I can look at it on the inside as looking kind of like this. And out. And some logic cloud in there that happens based on many ins and many outs. So CPU, an Arduino, it's all digital, right? It's got like 16 inputs you can use and some outputs, and it's got a processor inside. So if I were to hook a switch up to this, quick conventions, you can do this either way. So what I want to get is 5 volts or 0 volts going into the thing, or depending on the logic, there's 3 volt logic, 2.5 volt logic, 1.8 volt logic. I've even seen relatively recently, like on the output pins, some like 0.8 volt logic, really low voltage levels. So I have to switch power. So there's 2 ways to do this, practically speaking. I suppose I could do this, right? The double throw switch, and tie one up to 5 volts and one down to ground. And so when I push the switch, maybe it goes to 5 volts, and when I let off of it, it goes back to ground. and that gives me a signal in. That's kind of the hard way to do it. What you'll usually see, because this is cheaper than that, it's 2 components. Actually, I'm sorry. Something like this. So when I push the button, I get 5 volts in. When I let off the button, it can come back through this resistor, lose its energy, decharge that capacitor. Or vice versa, you can do it this way, 5 volts and ground. So when I push it, it gives me a low end, so you can wire it either way. What gets really clever though is with microcontrollers, you can get rid of this completely because you can turn on a little pull-up resistor in here. So that will give you 5 volts all the time, and when you hit the button, it inverts it. But if you don't have this, and this is where I was getting at, so if I put 5 volts in and I push the button, that'll charge that up. I'll let off of it. There's nowhere for the charge to go. So this will always be 5 volts, at least after the first time you press the button. And the decay time on it is hours sometimes. So one of the things you got to be careful of when you were doing our maker projects is we got to make sure there's a way to get this back to a known condition relatively quickly. So the next part, we'll start getting into some practicalities of using a capacitor and a resistor externally. Because what I was talking about, we get a bounce. So let's go back to this, this scenario. If I look at this in time, volts time, I see at some point I push the button, and at some point I release the button. Ideally we'll see this, right? What I'll most likely see is this. That's the bounce. Now, for a push button switch, this time here is usually on the order of 2 or 3 milliseconds. Not nanoseconds, milliseconds. So I want you to think about this. If I've got a processor, I think Arduinos run at 16 megahertz.
There's so many of them.
I think the standard Arduino Uno runs at 16 megahertz. So 16, 1, 2, 3, 1, 2, 3 hertz. That means that its clock is telling things to happen 16 million times a second. Do some quick math here, because I can't, 1 over 16, 1, 2, 3, 1, 2, 3. .5 nanoseconds is an instruction tick. I'm doing 16 million instructions a second. What happens if I press a button and this is going on for 3 milliseconds? This is an eternity to this thing. Let's see, if I 0.003 divided by 0.000 milli, 3 more zeros micro, 625, 48,000 instructions just happened. Now, I said, gee, I want to make a light bulb turn on when this happens. And I want the light bulb to turn off when it's not happening. That, you don't care. I can't see that with my eye. It's going to go right through. But oh, this is something that I've had to do here at work. I've got an actuator that's pushing something until it hits some sort of a limit switch, right? I don't want it to go any further than this. When it gets there, I want it to stop. It gets there, it goes bouncity, bounce, bounce, bounce. Oh, it's there, it's not there, it's there, it's not there, and then it went too far. So we had to debounce it. It's called debouncing it. Now, practically speaking, there's two ways you can do this. One is you can go in the software and you can just say, put a really big buffer and say, oh, well, if I saw one of these within, I know that it shouldn't happen this time. But what you're doing is you're wasting 48,000 instructions that you could be off doing something else, right? Or something along those lines. There's cleverer ways to do it than that. But you're wasting some number of instructions to be able to debounce that switch. Practically speaking, what you'll do is put a capacitor here. Okay, so remember that's going to store a charge. So when I push this switch down, it's going to take it a little bit. Instead of having this bounce, it's going to ramp up, and if there's any bumpity bumps in there, they're going to kind of do this. And when I let off of it, then it's going to drain back out that way. That's practically how you do it. And I will show you that on the scope out here right now, because we've been doing this for almost 45 minutes. It'll take a couple minutes to get out there and do this. So, just for practical, and we'll talk about what an oscope is and how it works. So I was telling you earlier, I accidentally bought a really good switch. So I'm going to show you this right now because it might be hard to get it to happen again. Let's turn the measurements off. There we go. So that's me shutting off a switch. So what this device does, all these graphs I showed, this happens in time. That's what this does for me. This is called an oscilloscope. It's an oscillation scope. But it lets me see what happens in time. So I've wired this up right here and push the button, get a light. Push it off. So this is exactly what I was talking about, right? No microcontroller here or anything, just me pushing the button. If I menu, I think auto is what I want. Run. So if I press the button, helps if I put this on here. I press the button, I've got 5 volts. I've got this set to 2 volts per division, so it's 2, 4, and a half would be 5 volts. So I press the button, it goes high, it goes low. You can sit here and click it really fast, all I want. But now, if I go to sweep, single sweep, so this is just running over and over and over and over. Now this is set up to catch a single. There's the falling edge, you see some glitches on it. So that tried to bounce but didn't quite bounce. Let me see if I can move this up so we can play with these things in time. I find that they generally bounce best on the falling edge, or worst. There you go. But that one looks nice, so it doesn't happen every time. So what it means is, if you get the exact same thing every time, that's easy to account for. If you get something different every time, that makes it hard, right? So here's a capacitor. And I've already got the resistor in line on this circuit. So I can just put the capacitor right there. We'll talk about breadboards a little bit. This is a nice way to prototype a circuit without having to spin the circuit board. Now, when I do this, it's not going to work at all. Thank you very much. Let's go back to, I know why. Thanks. Helps if I actually put the program in. Now, see what I was talking about? There's the capacitor discharging. So instead of being this nice sharp edge, And this is a function of the resistor and the capacitors that you use for it. If I go and look at the rising edge of this, it's actually not bad. Also, what you can see a little bit of overshoot right there. Let's see. I'll go there and take the position down. That's noise. Oh, fine. Okay, let me do it already. Fine. Going the wrong way. See that little overshoot right there? That's in the noise on this. That is from the inductance in the tracks. So we talked about how when you've got an inductor, it doesn't want to let current stop, but if you suddenly take away the path for the current to go, it's still pushing current. Ohm's law, the resistance just went to infinity, V equals I times R. R went to infinity, current stayed the same, voltage goes to infinity. The reality is there's nothing that's infinite here, so it sort of pans out. And the inductance is really crappy, so it's a function of how much inductance is there. So this is called a protoboard. Here we go. So this is called a protoboard, and the Makerspace here has one that's got 5 volts in it. I brought this one from home, and so this is a much better switch than I thought it was. I just thought it was a regular old switch, but I've been sitting here playing it. I could get it to bounce maybe 1 out of every 10 times. So if you look on here, you can see this the color codes on this resistor. But you can see this one that doesn't have color codes on it. This is a newer one. This is a precision resistor. And then this is my ground reference here for the scope. So we talked about ground. When we talk about ground, that's our signal reference for everything. So that's what it's comparing things to. So convention is, if you look at this thing, you've got all these pins. These are on 100 mil pitch spacing for your dips to go in, or whatever component you want to drop in. So here's a dip right here. This is one kind of a switch. Here's another kind of a switch. This is actually 4 little switches right here. So one of the things you can do is set configurations or something like that with these little switches when you're doing software. This is a light emitting diode. I guess we'll talk about those tonight too, and diodes in general here in just a few minutes. So you have a red bar and a blue bar. And generally, the blue bar is connected all the way across, and the red bar is connected all the way across, but there's nothing connected this way. If you look at these little holes, they're press fit, so when you push something in, it's got like little pieces of metal that are shaped like this, and when you push the pin in, it pushes them out of the way, but it holds it in place. So these 5, A, B, they're actually labeled up here at the top, A, B, C, D, E. They're connected. There's a little metal bar in there with a whole bunch of these little grippy tabs on it that connects them all in a line. So each one of them this way is a wire. And then down the side here, you've got blue and red, and in the middle, blue, red. So all along this is connected 2 lines. Generally, we use the blue as our negative rail, most often ground. Red is the convention for power. So right now I've got 5 volts wired into the red across here, and then I'm distributing it out on different lines here. So I've got power out here wherever I need it. And then I can come in here. This switch, for instance, I can not bend the leads when I pull it out. It has 4 pins on the underside. And when I press the button, it connects these 2 pins to these 2 pins. So this is basically a wire that runs across the inside of here. And you want to line the pins up with the 2 things. So Now I can drop a wire in where the pin was, or on the same line as the pin, and this thing here breaks it so I can have two halves of the circuit. Breadboard. These things, if you buy the Arduino Inventor's Kit or Maker's Kit, or they call it, it comes with a little one that's maybe that big. And so just enough to wire up little things and see what they do. And there's actually a piece of software out there I've seen that you can draw your circuit and it'll show you how loosely how to wire it on the breadboard. So you can just say, oh, put that right there and this here and that other. It's not perfect, but it's not horrible. Let's see, what else should we talk about here? Oh, is there any questions that you got on this? Oh, capacitors. See this one? This is an electrolytic can. So I talked about last week, some capacitors give a crap which way you line it up. Notice the white, oh well, the gray stripe has the minuses on it.
Mhm.
That's the negative side. That goes to ground. If you connect it up wrong, it can literally blow up. In fact, if you see the little cross on the top, little indentations that make the cross, that's a blowout valve. So if you overheat it, that'll blink out and actually explode, so it explodes up in a way. If you look,
So don't look directly at the capacitor. Don't stare at
these, if you got a problem on a board and it's drawing a lot of current, as often as not, it's a capacitor. And then you can look at these ones. This is another kind, but this is also an electrolytic. It's got the black on this side. So I believe that the black on this side is the negative side, but it's not always the case. So whenever you buy parts, look at their data sheet, they'll tell you what the markings mean. But since I see this wired up the way it is on here, on other stuff, I'm of the belief that that's the correct way. And if it blows up on me, I'm not out anything because I don't even know what that capacitor is.
And as far as breadboards go, you can wire the power into these guys.
Right.
And then you can have the banana plugs. That,
Right, so you can use,
I don't know if we have any laying around.
yeah, here you go. Maybe. All tangled up. That's a banana plug. So it's a 4 pieces of metal that are wrapped around a post like this, and they're springy. When you shove it in, it makes a compression fit. It doesn't want to come out. Oh, hey, that's hooked up backwards. That little guy's getting hot. We might see him explode here in just a second. God, man, that is a tight. Ooh, I can smell him too. He's gonna do something here in a minute.
Yeah, with the posts, you can put your power in and screw them down, so that's all disconnected. You don't have to worry about connecting power directly to the.
She's hot.
Some pliers over here.
You wanna touch him? See how hot it is? In a minute he'll burn your finger. In fact, I just dried my finger off. So, that's actually how you used to troubleshoot boards. You see if current go too high, you go around and start doing quick feet. Well, what's hot? And I actually burnt, I touched one and actually burnt the shape of the chip into my finger. It even had the little dot. You can see the little dot. I'm like, damn, it's all numb, burny feeling.
Done this a few times.
Hot.
So are you reconsidering that you might have put it in backwards?
It might have been put in backwards. Or it might be defective, one or the other. So that's been in this board for years. I just picked up this board this afternoon and grabbed it up. So my phone's in there. Let's see, what else? So let's go back and talk about LEDs then, and diodes. Well, digital, I can show you what you're doing in digital. You're actually you're decimating the image.
Mm-hmm.
So I said we talk about diodes. Diodes are really, really useful for a lot of things. The symbol of a diode is this. And the signs, and which way you hook it up is built right into the symbol. This is the negative side and this is the positive side. So, positive, negative. The most basic diode is called a barrier diode, I think. What's going on? Do you want the practical effect first, or do you want the short physics lesson?
I like physics lessons.
Sure.
All right, so there's two pieces of material in here. It's one piece of material heavily doped. And this side you dope with is an N and a P, so I don't remember which one's which, but it's usually arsenic and boron, I think. And what happens is the P side has an excess of holes, and the N side has an excess of electrons, because of the, we talked about the first class about electrons and valence and how conductors work and all this kind of stuff. What happens is, practically speaking, as you get closer to each other, the holes want to gravitate over here towards the electrons, and the electrons want to gravitate towards the holes. And here in the middle, where you stop, I need to draw a straight line. When these electrons come over here and these holes come over here, they combine, and here in the middle is sort of a dead zone. Now if you imagine that I put a positive voltage here and a negative voltage here, what's going to happen? So if this is electrons wanting to flow this way, right? So electrons are attracted to the positive voltage. Let's do this. And they come over here, and the holes are attracted to the negative. So what effectively happens is all your electrons go away, all your holes go away, and this depletion region gets big. And no hole or electron can go across that. So the practical point of what this is in fluid. Okay, if I go hook negative up here and positive here, what happens? Electrons are coming this way, electrons are repelled, holes are repelled. This depletion region gets smaller and smaller until it finally becomes effectively nothing. And a hole now can go over here and come around, and an electron can come over here and go around, and now it conducts. It's a ball valve for electricity. So if you think about, if you have a basement or something, or if you know hydraulics, you can have a pipe that comes up and it flares like this, and it's got a ball with a spring on it. And that's sort of how it looks physically. I mean, there's some couplings and stuff, but what happens if fluid flows this way, that ball gets pushed out of the way, and it continues to flow. But if fluid comes this way, it comes in, it presses that ball into the hole, and no fluid flows. That's what a diode does. Practical applications all over the place. And we can get back, we'll come back to this diagram because it helps explain some other stuff. First application, I've got a transformer. This is how we used to make power supplies. I've got 120 volts in, I've got 10 volts out. So it's a 12 to 1, right? So I've got this waveform coming in, and I've got, with reference to ground, I've got this waveform coming out. What happens if I put a diode right there? Now on this side of it, well, when that's positive, it conducts, but when it's negative, it doesn't. So now I get a waveform that looks like this. Now I've got a positive 10 volts coming out of there. Well, I've got a really ripply, nasty looking positive 10 volts. But now, if I come over here, we're going to throw some of this stuff together, right? I put a capacitor, a big capacitor there, and now, ideally, this comes up the first one, and kind of comes like that, whoop, 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 but I've charged it and everything's there. Practically speaking, now I put a load on it of some sort, some resistive load out here, and it does a thing that let's see, if I draw this, I end up with something that looks like that. So this is called my ripple. It's ripple voltage on top, and it depends on R and C and a bunch of other stuff. But practically speaking, I just made a really cheap power supply. Great, great. Now, that is the cheapest, easiest way to make a power supply. It's big and bulky because it's got this thing in there, and those things are usually that big, and they're made out of copper and iron, and they're heavy. So you don't see that in your watch or in your phone charger or anything like that. They play a different game. The next thing you can do with this, in a standard small signal, just a plain old diode, for you to get, just like this spring, you got to overcome that spring, right? To get that diffusion region small enough that current will flow across it, it's 0.7 volts. If it's silicon, it's 0.3 volts if it's germanium. And there's some other ones that are, indium gallium arsenide, whatever. They're different. They're all over the place. But these are the two materials you will most commonly see in a rectifier diode. And it's called a rectifier diode because we used to use them. That thing's called a rectifier. It takes away 1/2 of the negative signal. You could do another step here, actually. I can do a diode there, and I can do a diode here. So that first one was called a half-wave rectifier because it does this. You get half of your wave. This is a full wave rectifier. Now when this goes high, so when this goes positive, that goes through. When it goes negative, that's actually a positive voltage here and a negative voltage there. So current flows this way and comes up, and it can't go that way. So now you get a full wave rectifier. Practically speaking, less capacitance gives you the same amount of you can use the same amount of capacitance but get less ripple, more power delivered, less power lost, things like that. And then there's a fancy one somebody figured out that is called a full wave bridge, which does an even better job and handles more power. And it's 4 diodes. Think about this for a second. There. It's been a long time. I think it's like this. Current comes in, goes there, goes out, comes back. Yeah. So current flows this way, out, comes back in, down that way. So it acts like 2 switches. And then when currents go in the other direction, it comes in. Let's see. When things are reversed, then I think I got one of these backwards, but that's the way it works. The last thing that I personally use a standard diode for is we talked about originally if you've got 2 power supplies. Oh my God, don't ever do that to them, because this is a 5 amp supply and this is a 5 amp supply and I need 10 amps out here, because the truth is this 5 volt supply and this 5 volt supply is really like a 4.9 and a 5.1, And so that means current's going to flow like that. I'm just going to blow things up and it's not good. This voltage will be the higher of the two. So if this is 5.1 volts and that's 5 volts, this is going to be 4.4 volts coming out. Because you got to subtract that minus 0.7, right? So current flows this way. So 5 minus 0.7, so I have 4.3, fine.
You said 5.1.
Yeah, I said one's 5.1, but I've got 5 written down, so I'll stick with that. So I get 4.3 volts out there, but what happens is I draw current. Remember, these things, these are ideal, right? So the truth is, there's a little bit of a resistor in there. As I start drawing more current from this guy, his voltage will start to droop a little bit. And there comes a point where they balance each other out and they're both supplying current. Unless there are huge differences between them. If they're really close, then I can get more current. Or I've got redundancy. If one of them decides to die, I've still got this one feeding. And that's what I use them for mostly, is redundancy. I'll take two 5-volt supplies, plug them together. This is called a diode OR. Diode OR. Because it lets this one or that one through. And it keeps you from letting the smoke out. Now, the next, so this is a barrier, just a barrier diode, also known as a rectifier diode. There's multiple different kinds of diodes. You will see Zehners, and a Zehner looks like that. And what a Zehner does, it's actually made to be hooked up backwards. You hook up a resistor and the Zehner. So this is a ballast resistor, and you have to look at the data sheet and you say, oh, I've got 10 volts here, but I want, I don't know, some reference that's like maybe 3 volts out here. So you'll choose a 3-volt Zehner, and they'll have a current rating that is like, I don't know, 5 milliamps, something like that. So 5 milliamps, and now you do your math, right? So I know that this is going to be 3 volts out, 10 minus 3 V, that's the V drop here, so that tells me I'm losing 7 volts right there, right? So 10 and 5 milliamps going this way. So that tells me that to get 5 milliamps through 7 volts, V equals IR, 7 equals 0.005 R equals, I don't know, I can't do math in my head. 7 divided by 0.005 equals 1.4 kilo ohms. And now I've got a 3-volt reference out there. The truth is, as soon as I put a load out there, you're going to change. There's going to be a little bit of current flowing that way, so it's going to change. So you're going to do a little bit more math. But this is what I was talking about with the Kirchhoffs a while before, where I have some supply that's a 10-volt supply. I've got my resistor. I have another voltage source here, and I play this game. Right? So I know he's not a voltage source, but I treat him as one for this. 3 volts. So again, we do our math. We start from here. We say minus 10 plus IR, because V equals IR, right? Plus 3 volts equals 0. So 3 plus IR equals 10, IR equals 7. That's what we did right there, right? And we set 5 milliamps to I. So I equals 5 milliamps. So 5 milliamps R equals 7. R equals 7 divided by 0.005 equals 1.4 k ohms. That's why you want to do that. One of the reasons. Let's go to the next. The diode that you will see most often, I almost guarantee it, is an LED. An LED, symbol for an LED is this. Let's see. Light, emitting, diode. Don't say LED diode, that's annoying. Light emitting diode. Same thing. Except, as a rule of thumb, most LEDs, this voltage is 1.2 volts. And you can't just hook them up. If you just hook it up to a 9-volt battery, it's going to blow it up. I mean, you get one little flash of light and it'll be done forever. So you have to put the ballast in, and most of them, their maximum brightness, it depends on what you look at, but they're like 15 or 20 milliamps. So again, we do the math, we'll say 20 milliamps. So 3 becomes 1.2, 1.2, and let's make this 5 because we would normally have a 5-volt supply, right? Our Arduino uses 5 volts, the logic is 5 volts. 5 IR is 3.8, and now instead of 50 we've got 20 milliamps. So divided by 0.02, I can tell you what that number is, but I'll get it wrong. So 3.8, 3.8. Divided by 0.02 equals, not times, 3.8 divided by 0.02 equals. Do you remember what I said 2 weeks ago? About 200 ohms. 200 ohms is probably the most common resistor you're going to see because we always use them for LEDs, or 220, 230, 300, somewhere in there. So again, same logic, it applies. This is the minimal math you need to do. If you know that you're always going to be using a 5-volt supply, and you know that most of your LEDs are about 1.2, invest in a bunch of 220 ohm resistors, and they'll get you 85 or 90% of your projects done for little lights.
And I found out the hard way that different color LEDs have different voltage.
They do often. They do often. And it's not just that. The energy that's going through them, red is, for instance, is a lower energy photon. So if I put the same amount of energy into a red LED, assuming everything else is equal efficiencies and that kind of thing, it will give me more photons out than a blue one will. Because blue's high energy. I got to get more energy to get a single photon. So what that practically means is that most often a red one will look a lot brighter than a blue one at the same energy. But blue ones are never the same energy. They're all, if you ever see a blue one, they're like, oh my God, that's really blue. And it's because they're putting a lot more energy into them. So you've got to play games there too. You can find some really nice packages. Adafruit sells some that are I'm not sure which way it's This is the little can. This guy, he's got a flat side and 2 legs. One's a little longer, I think that's right. And it comes up inside to a flag. So that's, let me grab one of these diodes real quick. Let me grab
Yeah,
one
I
of
was
these.
gonna say.
Let me grab one
Yeah.
of these diodes real quick. Okay. Well, I got the length wrong, or those are the same. That's certainly negative. All right, so look at that guy. Number 1, so that is a TO5 case, I believe. So that's, if you see something, the case is a TO5. Number 1, see the little flag inside of it? One side's got like a little triangle, but the other one looks a lot like a flag. That's the cathode, the negative side. That same side has this flat face. That's the negative side. And usually one lead's longer than the other. And if I remember right, that's the negative side.
Yeah, I think that's right.
I can't remember for sure about the length of the legs, but
There's definitely one usually longer, but
yeah, there is, and I think that's the negative. So, but what they'll do, Adafruit, for instance, has, you can buy these guys. And I think they've actually got the resistor built into them too, but I wouldn't swear to it. So it's like that guy, only he's got 4 legs sticking out of the bottom, and one's a red, one's a green, one's a blue. Red, green, and blue together. You only got 4 because you got to have ground coming back.
I think I've seen ones with 3, but I'm not sure how they.
No, there are some that are like red and green, so you can like
Get yellow, yeah.
Well,
But
you can get yellow, but you can say, oh, bad, oh, good,
Right.
oh, somewhere in between.
Yeah.
And that's, yeah, they do exist, but that's the reason for them,
Sure.
is because you want 2 colors. They're just
Mhm.
indicators. But with red, green, and blue, we all know you can make the whole, not the whole color spectrum, but you can do a lot of the color spectrum. We can talk about that someday if you want, but I'll have to get some reference material out for it.
Well, with light, not with paint.
I know.
You can't get good yellows. You actually have. I think Sony. It was either Sony or Samsung was bragging about their with yellow LEDs.
Samsung with their TVs, they were showing off how, their little diagram shows red, green, blue, and yellow.
Yeah. And so we'll get into it a little bit. If you look at your color spectrum, there's a color chart. It looks kind of like a Star Trek symbol. It's not quite that way, it's round-ish. And these are the axes, so I'm going to get this completely wrong because I don't deal on this usually. So like this is red, this is green, and this is blue, and this is mapped to the sensitivity of the human eyeball. So if I've got, it runs on a curve, and it looks kind of like this. Actually, it looks kind of like this. So like here is white. You know, so if this much green and this much red and that much blue is going to look white to me. Blue greens are out here. Oranges are red and blue are in here, and red and green is yellow. No, blue and green is yellow, sort of here. But where our eyes can actually see is more of a thing like this. That's the wrong shape, but it comes out more. And so we don't miss a lot of color here on the red-blue side, on the purple side, the violets, but we're losing a lot on our televisions out here. So they put a yellow, you can kind of stretch this out like there by putting a yellow out there. And now you get a great big change in color depth. All these different colors you can see better now. So what it really does practically is it make your yellows more yellow and your greens. Because of this, you can get some better shading on your greens and blue green, whatever the hell that color is. So which I guess is yellow, right? Blue and green and light makes sort of yellow. So that's what's going on there. I've actually seen some LEDs now that have red, green, blue, yellow in them, so they're 5 lead. But what we also have available, Adafruit and Spark Fun, and choose your vendor, do these. It's a little chip. It's a neat little chip. It's got power, it's got ground, plus, minus, and it's got signal. And you use serial commands. We talked about a serial stream of data. Inside it's got a little register and then a little transmitter to retransmit as you go, so you can just put a whole gob of these in a row. And what it is, it's broken up into 3 pieces, red, green, blue. And you send your data down. So if you've got 10 of these, you'll send red, green, blue, red, green, blue, red, green, blue, red, green, blue, red, 10 times of red, green, blue. And it'll load it all up. And then you do a funky little thing on your timing. You go, and it says, hey. And it sets them all, and you can have all the colors of the rainbow out there.
Yeah, that's what your eyes are like. Did a hat for her that had animated eyes on it, and it was an 8x8 grid of bicolor LEDs.
The name for this thing that I've seen most often is a Neopixel.
Yeah.
Neopixel.
This wasn't a Neopixel one. Those are the tiny little ones that you can get in the circles or the lines or all the different shapes. This was a more traditional LED, but 8x8 grid, bicolor, and you, programming wise, you send the data and then you say refresh.
Yeah. And when you get onto the Arduino anyway, there's libraries for it. So you don't have to write your own code. You just say, I want to do this, and you read how to do it and follow some of the examples in some of the other code.
Yeah.
And make stuff happen. So I hit everything that I said I was going to talk about tonight.
Cool.
It's been an hour and 15, hour and 20 minutes. So I can talk about some other kinds of diodes that I know of. There's, I mean, we've covered the ones that you'll see completely, you know, more often than not. So Zener, sometimes people call them the voltage reference diode, just a standard diode. This is the way they look. The symbol is usually D, D1, D2, D3 when you're doing a schematic. This is an LED. There is a fast recovery, I think is what that's called. There's a, where's that, a tunnel diode? That might be a tunnel diode. There's a, this is how often I use these, right? It's, there's a Shockley, I think. And a lot of these, what it is it's how fast they switch, and some of the they're tuned for special things. A tunnel diode can actually be used as an amplifier because it has a nonlinear current to voltage response curve, so you can twiddle the voltage a little bit and get a big voltage change across it. I've not seen one of those used in 30 years. I mean, I was taught how to do it, and I've never seen one used since. LED, Zener, plain old diode, tunnel, Shockley, and then a fast recovery. When you look at electrons, do not move at the speed of light. Electrons move pretty fast. I don't remember how fast, but pretty fast. The signal propagates at near the speed of light. But so when you've got all these physical things going on, you know, these electrons having to jump back and forth with holes and whatever else, they do things to try and speed them up or get that voltage down low. it's called the switching time. So like if you look at an LED, is an easy way to, oh, here's the other one that I'm missing. This is a photodiode. That one you'll probably use every now and then. So the way a photodiode works is not to be confused with a cadmium sulfide detector or a pyroelectric detector. Different things going on. In the end, the result's sort of the same. But you hook a photodiode up backwards, again to a ballast, usually to some voltage, to ground. And when light hits it, it breaks over and conducts. The truth is, every diode will do that. So if you're using those little diodes, you'll see them. Usually they're germanium, usually they're fast switching. They have a glass case on them. So just like this light emitting diode, you can look at it and you can see the junction in there. In fact, it'll happen with these too. When light hits them, they conduct.
Is it the kind of looks like a grill sometimes? I think those are the ones.
No, that's cadmium sulfide.
Okay, that's what's in the rat.
That's that is a photoresistor.
Okay.
As light falls on it, its resistance goes down. It's a different mechanism.
Gotcha.
That's what it comes down to. What happens in our there's also a
What makes the rat shriek?
a varactor, which is a voltage controlled capacitor. And so while I'm doing this, it falls sort of the same way. So I look here, and I've got my diffusion region, right? And my P and my N. I've got my little electrons floating around over here, and my little holes over here. And they can't go anywhere. And remember, when I put the voltage on backwards, positive here and a negative here, it caused this diffusion region to move out. So first off, we talked about a capacitor, right? It's two parallel plates that are some size and some distance apart. So it was a function of area, which is width times length, times some constant, which is the dielectric constant of this, capacitance equals, and its distance over the plate. So the further apart those are, your capacitance goes down. If they get closer together, it goes up. If I put this voltage on here, this diffusion region, these edges of it, actually act like capacitive plates. And it's not a big change, but this is how, I don't know if that's what they still do, but it's how they used to make voltage controlled oscillators. So if you wanted to tune from 5 megahertz to 10 megahertz, you were changing a little voltage out there that was causing the diode to move out. Actually, what they used to do a really long time ago was they used an air-gapped capacitor. If you've taken apart an old radio, you've seen it. It's got a knob out here on the end, and it's got big metal, damn things are that big around and that long. It's got big metal plates that are fixed down, and then in the middle, so these are not connected. In the middle, these are. And if you look at them from the side, usually it looks something like that with your knob going through and the other half up here. And as you turn it, the plates slide into each other like this. And so as more and more plates come in, more and more capacitance, change your tuning. I don't have it anymore. I threw away my last one like 10 years ago or 5 years ago when I cleaned out my own historical electronics museum. But the other thing that happens here is we should know from high school physics and chemistry and any other that we've had above that, is if I have an atom with a nucleus and an electron floating around here. So I guess that's a hydrogen atom, right, in this particular case. So it has an electron and a hole. But what happens is if light comes in and hits that guy, if he absorbs it, he jumps up a couple bands. But if there's enough potential out here, he can jump up that band and then get swept away. He's gone. And then eventually some other one will fall in. And this is part of how an LED works, is when that electron falls back in, it gives off light. We make him energetic by putting electricity on him. He pops out of his valence band, or he pops out of the valence band up into the conduction band, and then when he falls back down into the valence band on a different one, he gives off a photon. Woo! Light. The reverse happens too. Light comes in, he can pop up. If there's a voltage difference there, he can be swept away. So that's my this diode. And usually I'll hook him up backwards. If I hook him up forward, he works just like a regular diode. If I hook him up backwards, he detects light. And again, that's true of all of these. If they're in a clear case, they're picking light can get in. So light comes in, an electron pops out, floats away. He conducts. So I can detect the presence of light. The one that you're talking about that has the little grid on it, like looks like this, it's usually round.
Yeah.
That is cadmium sulfide, CDS. And that is a change in resistance. So they might change from 100 k ohms down to 10 k ohms under varying conditions of light. What you see with these is more and more current flows. So depending on how you're using it, it can have a similar effect. But we get back to turn on times and turn off times. For cadmium sulfide, they're slow. If you wanted to flash a light and do Morse code with it, you might be able to detect Morse code at the rate that I can ham it, which would take a long time because I don't remember it anymore. The on time and off time for these things, for an LED, so if I turn it on and light comes out and light comes off, that time here, T on, is about 2.5 nanoseconds. It's on. With a regular LED, if you set your stuff up right and you get them close together so that they get good brightness, you can push gigabit per second data rates. In fact, fiber optics, right? I mean, they've got them tuned really, really fast, and they're pumping 100 gigabit on some of the stuff. They're playing games with multiple colors usually, but anyway.
Cool.
Did I bore the hell out of you guys tonight?
No.
Anything interesting there? So let's see. So what did we talk about? We talked about how to use an LED. We didn't talk so much about how to use any of these, just some quick what they are. We talked about switches and practical uses for inductors, capacitors, especially with switches for the capacitors and resistors, and how to ballast out your LEDs so you can light them and not let the smoke out. Now the truth is, one piece of sort of truth is on your microcontrollers, most of them are made so that even though they might have a 5 volt high output, they can't source more than 25 milliamps. So you can drive the LED directly, but number one, you're drawing more current than you would otherwise, so things are going to get warm, your batteries are going to run out faster, and two, you're kind of stressing the thing, because that LED will draw a lot of current, and the only thing that's keeping the microcontroller from supplying that current is that it can't, and just because it's either designed to current limit or it's got a high resistance. But regardless, that means it's giving off heat. So you're wasting, I don't know how much when you do that. I don't know how their current limiting circuit works, but it's something that you have to take into account then when you're doing your design and you figure out how much current you want to.
And I get the impression that the Pis have essentially the bare minimum. They're meant to be as inexpensive as possible. So.
And the Arduinos, all of them.
Yeah.
There's a reason you can pick them up for $10.
Yeah.
Mass production's one of it, but I mean, I've done some circuit boards that are, I wouldn't say similar complexity to a Pi, but about the same size. And when you go to a circuit board house, they charge you by the square inch and number of layers. So, you know, the Pi board is, I've bought some that are similar size from Japan for $1 each. Not Japan, from China. Put my own design down, double-sided, $10 for 10 of them, plus shipping, so maybe $15 for 10 of them. And then, so that means that, you know, at $1 a board, and now you start talking all those little parts. When you buy them by the million, you get the prices down, but they rapidly add up. I made a board for work a couple of weeks ago. It was about the size, it's this size. I got them, I used Oshpark, which is a rapid prototyping house here in the US. You can get 2-layer boards back in like 3 days to a week. I think they charged me $10 a board, which, you know, that's not what a real production price is, but I think the components on it, my first cut of components was over $100. I was like, holy cow, those are expensive components. So I went back and looked, and I got, you know, made some choices for alternates and got the prices down to like $40 a board or $30 a board right off the bat. It was like 2 or 3 components were hugely expensive. One last thing, since we talked about caps kind of heavily tonight and using them for these kind of things. Your capacitor, we'll talk about this next time, so send me an email to remind me or something. There's 2 things. There's a time constant, which says how fast, you know, if I put too big of a cap and too big of a resistor on there, I'll press that button and an hour later it'll finally get high enough that the microcontroller registers it as a high. And then when I let off of it, it'll be another hour before it gets down to the point where the thing gives a shit, right? But this is a sort of a safety thing. Your capacitor, I don't need to do that, that's redundant, has a voltage rating. De-rate them. So if you're using 5 volts, go off as much, anywhere from 20 to 50% higher. So you don't want to use a 5 volt capacitor. You want to use no less than a 6 to 7 volt, and go higher if you can, if it fits in your space. What happens is they get higher voltage, they just get bigger. So, and the reason for that is most capacitors are in the 10 and 20% range of, you know, plus or minus 20%, and that has a direct effect on charge capacity. So if they're on the low side, they can overcharge, and that can cause them to go bang or heat up like that one did out there. So that might be the other thing. Those might have been 2 volt capacitors. I don't know. So when you buy, that's one of the things you want to keep in mind. That if everything I'm doing is 5 volts, I want to use 6 or 7 volt capacitors or whatever, or nothing lower than 6 volts, and then you can do your DigiKey or Mouser search. That was my phone on that, and that'll get you the right range of stuff. I think that's it.
Cool.
Capacitor safety.
Yeah.
It's going to be like 4 videos tonight or 3.